So lecture 12, well, it might look complicated, but it's actually the same thing. So the backbone for these lecture is still superposition. So that means when you have arbitrary periodic inputs, you want to convert those that periodic input into some inputs that we are more familiar with, and then eventually you sum together those solutions. So for lecture number 2, we're going to talk about periodic inputs. All right. So before doing that, there's one key thing we need to understand, which is called Fourier series. So the meaning for these, for Fourier series, is actually just a simple equation, which I highlighted in this box. If you look at these equations, so A0, AN, and BN, they're just constants. So N is an integer. And then omega t, we call that the fundamental frequency of the input of the signal. So this fundamental frequency is just 2 pi divided by t. And then n times omega t, you can call it a harmonics or higher harmonics of the signal. So your t is just the period of your signal. So whenever you have a periodic signal, you can always use the so-called Fourier series to convert it into infinite number of harmonics or infinite number of sines and cosine functions. So once you can decompose your input, we already know the harmonic response from section 2. So in section 2, we talk about how to calculate harmonic response. So that means we can find the solution for each individual sine and cosine functions. In order to find this final solution for ft, you just need to sum all these solutions together. So if you look at your slide number 4, so that's it. So that means in this lecture, the key point is how can you convert ft into a bunch of sines and cosines. All right, so here is the equation. That's how you find A0, AN, and BN. But then, actually, we can simplify our discussion just based on the property of your ft function. So one way to do it is if it's for odd function, that means, okay, so I think I should ask a question here. Do you know what is an odd function? So what is an odd function? Well, let me use a math equation to describe that. So if your function is odd, that means your f minus t equals to minus ft. So that's the definition for an odd function. And then if you're more familiar with plots, that means if you take the negative section and then rotate it around the origin by 180 degrees, then this red line should overlap with the positive section. That's the concept for odd function. So if your function is odd, that means each component in the function should also be odd function. So in other words, you shouldn't have any cosine functions. So cosine function in Fourier series should disappear. Because the cosine function cannot, if once you have a cosine wave in this function, and then the function can never be odd function anymore. So in that means all the cosines or all the A terms should be 0. That's related to an odd function. Similarly, we can define what is the even function. Your even function is f minus t equals to ft. So if you're more familiar with plots, that means in a plot, so whatever on the negative side, if you flip it with respect to y-axis, then you get overlap. So this is how you find if your if your function is even or not. So if your function is even, that means you cannot have any sine terms in your Fourier series. So that means your Bn should be 0. So based on this, if you want to do Fourier series for a periodic input, the first thing you need to do is to see if your function is odd or even. So if they do have this special property, that can simplify the discussion by quite a lot. And I posted, I think I provide you 3 links on Blackboard. So in that link, there is a series of videos explaining how to calculate Fourier series. So make sure if you're not understand what I'm doing here, so you can go back and check those videos. And here I'm going to give you an example about how to do Fourier series, how to calculate that series by hand. All right. So we have a sawtooth function or triangular function. So in this case, we know the period is t. Your t is 5 seconds. All right. So if t is 5 seconds, then we can rewrite our force function. That is 0.8 t minus 1 when t is greater than 0, smaller than 2.5 seconds. And then it's 3 minus 0.8 t. T is greater than 0.5, smaller than 5 seconds. All right. So that is our ft function. So first of all, your system is it odd or even? Do we have a special function here?
Wouldn't that be an even function?
Yes, right? Because if you continue drawing these, it's actually symmetric with respect to your y-axis, right? So that means we have even function. So let's go back. If we have even function, that means Bn is 0. That's nice. We only need to calculate A0 and An. So what is your A0? Oh my gosh. Personally, I don't like Fourier series because a lot of integration. So your A0 is 2 over period, integration from 0 to period. Oh, okay. 2 over period integration. That's your ft dt. And then let's plug your t back in. That's 0.4 from 0 to 5 seconds ft dt. Because your ft is a piecewise function, so that's why you have to do your integration piece by piece. So let's record it. Let's expand it. So the first part is from 0 to 2.5 seconds. In this case, your ft is 0.8 t minus 1 and dt. The second part is from 0.5 to 5 seconds to the 3 minus 0.8 t dt. And then this entire thing times by 0.4. So that one is simple because whatever inside of the integral mark is just a first order equation. So you can easily find that. And then eventually the solution is 0. I can guarantee you that. So actually A naught is the average value. Of your signal or function. I should say 2 times the average value because there is a 2 on top. So in this case, because if you focus on one period, this is one period. And then if you calculate the area, so this is negative, this is negative, this is positive, this is positive. So the positive and negatives, they strictly cancel out. So that's why you can see within one full period, the integration, the value should be 0. So that's why the average value for this function is 0. So you don't even have to calculate this integration. You can directly tell that's 0. But then how about, let me start another page. Then how about AN? AN is complicated, is 2 over t, 0 to t, cosine, okay, ft cosine n omega t, t dt, is that correct? Yep. And then what is your omega t? Your omega t, as I mentioned, is 2 pi divided by t. That's 0.4 pi. That's your fundamental frequency. And then eventually your AN is 0.4 times 0 to 5 seconds ft cosine n is an integer, so you leave it there. And then omega t is 0.4 pi t dt. So you have to calculate these integral. And then remember, your ft is piecewise function. You have to write your integral in by part as well. Is 0.8 t minus 1 cosine 0.4 m pi t dt plus the second section from 2.5 to 5, 3 minus 0.8 t cosine 0.4 m pi t dt, and then you multiply everything by 0.4. And then the challenging part becomes how to calculate these integrations. When I learned Fourier series 15 years ago, gosh, we have to go back to find the integral table and then do all of these by hand. But then I noticed that MATLAB can help us to do integration about 2 years ago. So I no longer recommend my students to do these by hand. So let's do these using MATLAB. All right. So I already posted one example. It's called Lecture 12 example on Blackboard. Make sure you check it out. Here I'm gonna briefly explain what to do. Oops. right? All right, this is the MATLAB page. Let me zoom in. So we need to do integration. And then we know that we have some symbols in the equation. They're n and they're t, right? We don't know. The time is n. And then our equation is a I don't want to type in everything. I'm just going to keep copy and paste. Perhaps not. Okay. So what we're doing here, so the second line, you assume n is integer. Okay. You can directly use the assume function. Assume your n is a specific type of variables. And then your an is 0.4 times integration of the function from 0 to 2.5 seconds. So let me quickly add some comments here. So if you want to use your integration function, then you have input 1, input 2, input 3. Let me zoom out. All right. So I'm going to explain what your input is. Your input 1 is the function to be in for integration. And then your input 2 is the lower bound. And then your input 3 is the upper bound. All right, very, very natural, right? Not a lot of like, I don't think it's really hard to understand. So you just put your equation in the first one from 0 to 2.5, the second one, 2.5 to 5. And then let's click run. So that's your final solution. Gosh, it's really complicated. But whenever you do symbolic analysis, so once you get a solution, you always want to try luck by using simplify. All right. So this simplify function is able to, MATLAB is trying its best to simplify the solutions it provides. I think they should build in the simplify into the original equation, so you don't have to manually add this. So let's calculate it again. Eventually, your an can be written in this format. So this an is exactly the same as the first one. It's just MATLAB use simplify to reduce, like to convert these complicated expression to these short and nice expression. All right. So that's easy, right? So let me write this down. -1. Right. So any questions related to MATLAB? All right, cool. So if you want, I can give you like a few examples. Like since we don't calculate an or a0 here, let's calculate a0. What is our a0? Let me copy and paste from the lecture notes. Your A naught is 0.4 times integration from for point A t minus 1. And gosh, a lot of brackets. So the first one is lower bound is 0, upper bound is 2.5. Right, so that's the first part. And then the second integration is for 3 minus point A times t. Lower bound is 2.5, upper bound is 5. All right, so that should give you your A naught. So your A naught is 0. So if you don't want to use the symmetric property, you can also use, if you want, you can also calculate your Bn. We already know that Bn is 0, but I'm going to leave these for you after class. All right. Well, perhaps not, because we already have An. Bn is relatively easy. Let me copy and paste. So your Bn, you just replace all the cosine by sine. That should be it. Let's give it a shot. Oops, your Bn is not 0. Let me try to simplify this Bn. Yep, then you see your Bn is always 0, right? So if you know how to use MATLAB, man, that's gonna save us, I would say save you hours. So make sure you know how to use MATLAB to find Fourier series. Otherwise, your exam 3 you need to spend like 3 more hours on your exam 3. So here is the example for, I just posted, okay? And then also I posted homeworks 1 and homework 2. So there are 2 more examples. All right. No worries, I'm gonna share these codes. I'm gonna save it as lecture notes. I'm gonna post these online so that you know these lines. I think that's really important, right? No worries, I'm gonna post these on Blackboard right after this, so you don't have to copy and paste it. All right, so we know Fourier series. We know how to convert up to this point, we know how to convert a periodic signal into a bunch of sines and cosines. So once you have that, let's assume we have a second order system. Your Ft is periodic. So that means we can convert our Ft into A naught plus summation of n from 1 to infinite. So An, gosh, I forgot. Is it cosine? Yep. Cosine n omega t plus Bn sine n omega t. All right. So that means we just need to calculate the response. Then we have n subsystems. Actually 1 plus n, because the first one is always due to the initial condition. And then we solve the system due to each harmonic response. And then we eventually lump them together. But then there are a few issues. The first issue is n equals to positive infinite. Man, how can we calculate infinite number of harmonic responses? There's no way. So that's why we assume, so in practice, you can pick an upper bound for n. Like in the homework, I assume n is smaller than 10, or you can try n is smaller than 20. And then you can compare, actually the difference is really small. So in other words, it's okay to ignore the terms when n is large. So it's okay to ignore those terms when n is large. All right? So why? Why we can ignore those high order terms? So there are two reasons. The first reason is your AN and BN becomes very small when n is large. If you remember, like our previous AN is 4 minus 1 n minus 4 over n squared pi squared. You can see that there is an n squared in the denominator. So as n increases, your AN almost becomes 0. So eventually your AN and BN becomes 0. So that means the contribution from the high order terms, or the amplitude for the high order terms, they're relatively small. So I would say that's almost always true in practice, because it's really hard to generate large displacement at high frequency. All right. The second reason is for damped system, the impact from AN and BN is small. Then we have to go back to our Bode plot. Like in this case, our Bode plot. So that's your omega. In this case, it's actually n times omega t, right? That's your response. That's your nth order response, xnt. If we remember the force transmissibility, or in this case, x over f, that's actually compliance. It's something like these, right? So when n is really large, so we're operating along these lines. So if you look at the Bode plot, the magnitude of the Bode plot is almost negligible. So that's also very true in practice. That means most of the systems are resilient to high frequency. Like, assuming that yourself is an actuator, you're holding like a 10 kilogram weight on your hand. If you want to lift it in 1 hertz, you might still be able to do it. But then if you want to lift the weight in 1,000 hertz, like doing 1,000 times per second, I don't think a human being will be able to achieve that, because it's really hard to drive a system at high frequency. So the same thing, so that explains why we can ignore the higher order terms, because those high frequency forces, they barely move your system that much. So we can just ignore their impact. All right. So if you have a cutoff frequency or cutoff harmonic, let's assume it is n equals to 10. If n is smaller or equal than 10, then eventually, if you go back to here, you can make sure it's no longer infinite. You can just use 10, just pick the first 10 terms. And then remember, this is the harmonic response due to cosine input. This is harmonic response due to sine input. For each sine and cosine input, you have these equations. They might look weird, but if you go back to lecture 9 and 10, I believe, I would say 8, 9, or 10, I just forgot. Basically, section 2, when we talk about harmonic excitation, so each one is one harmonic response. So that means you have your amplitude, you have your driving frequency, you have your phase lag. And then this term is introduced by A naught, and then there's a static force because your A naught is a static force. So that's your static response. And then the first one is always due to your subsystem 1, which is initial condition. As you can see here, that's just free vibration, right? That's just free vibration for underdamped system. That's a static response due to static force. And then eventually that's all the harmonic responses due to cosine and sine waves. As I said, you don't have to go to infinity because when n is greater than a certain number, so these responses are almost negligible. So usually you can try. So in practice, if you do want to use this method, you want to gradually increase your n. For example, you can start from n equal to 5, n equal to 10, and then up to one point when you see no increment or no changes in your solution, then you can stop there, right? I think there's a lot of things to digest. Yeah, try to work on the homework, and then I believe next lecture I'm gonna begin with these homeworks. All right. So, any more questions on this? All right. If no questions, let's call for it today. And then, as I mentioned, pay attention to your grades on during the weekend, and then see you on Monday. All right.